All right. Hello again. Welcome back. I'm Agent Ultra, and on this stream, I am here to hack on some stuff in the programming language called Haskell that we all know and love. Or at least I enjoy it, and I hope you will too. Or at least maybe you'll just enjoy hanging out, learn a few things, whatever. So yeah, let's get into it. The past few weeks I've been working on a little project to implement this paper I saw. I kind of want to see it working in action. Couldn't find a library based off of it or anything like that on Hackage, so decided to take a chance at implementing it myself and see if I can't learn something from it, and maybe find something useful out of it. And that's how you do. You learn things by experimenting sometimes. So, without further ado, let's see, where did I put the PDF project I called Disco? Maybe in downloads? No, documents. There we are. So the paper is called Monadic Prompt Lazy Assertions in Haskell. This is like a big fancy title. Maybe it's not that fancy to you, but the general gist of it is that we have like the assert function in Haskell, and it's pretty okay, but it's eager in the argument that evaluates that Boolean. All right, so you give it an assert, you give it a Boolean function or a Boolean value, some kind of Boolean expression that you want to hold true. And if it's not true, then you get an error, a runtime error, an IO exception. The idea behind this paper, as far as we've been learned so far, is that we can write an assert that is lazy in that argument. So if you have a rather large data structure, like a big list or something that's infinite or recursive or whatever. Well, infinite is probably not so great, but if it fails, it'll fail right away rather than evaluating the whole structure, right? Which is what you'd have to do in an eager assertion, an eager language with an eager assertion, right? You'd have to have that data structure in memory to test that assertion on it. So this one does it a little bit differently. It's a little bit more lazy, so that it only reports up to the failure if it fails, and then doesn't compute anything else. So it doesn't evaluate any of the rest of the data structure if the assertion fails. And I thought it might be neat to check this out. I was watching some stuff about Tiger Beetle and their approach to programming. Their coding style guide, which they call Tiger Style. Fun little name, but one of the tenets of it was, or one of the ideas they had, is to always run their assertions even in production, because they want their system to fail and fail fast. They don't want bad states to be propagated and for programs to continue in bad states. Right? So, exploring the options out there in the Haskell land, trying to learn a little bit more about how this could fit into functional programming. Can we use it? Is it useful? Are there other better approaches for us? That sort of thing. So, to the code. Yeah. I'm going to go projects, Disco. Okay. We have our library file here. And I believe we were just at some bits where we were trying to implement maybe new monads. What is our type error here? Okay. It's kind of an interesting thing to do if you're programming in Haskell and you're working on a project and you got to put it down for a little bit. Leave a type error up. It kind of lets you pick up where you left off and gives you a thread to pull on. Doesn't always work, but sometimes it's a good idea. Okay, so we got a bunch in here. F's, X's, and we've got this try thing. This is the implementation of parallel apply. I believe this is from the paper. Let's see, the assertion monad. Respecting laziness, non-determinism. Generating our eval trees, and now we're in promptness. So slight optimization here with coroutines and stuff. What they introduce. And we were... Where were we? Here, I think? No. Here. Maybe. Okay, F's, because F's is not a collection. Okay. I miss this one here. Eval should have one argument, but has been given none. Oh, that because that needs parentheses. And this one shouldn't have term value, different number of arguments. Okay, and here we expected eval tree. We're getting eval tree refs from suspend. Because of condeval? Condeval, maybe. That's a recursive call. Who's demanding this? Deladris, what's going on? Nice joke. Thanks, dude. Welcome to the chat. Welcome to the stream. Hello, Fonny X. How's it going? Welcome, welcome. Thanks for coming by and hanging out with me. By the way, if any have any questions, feel free to jump in and ask away. Well, it's been nice seeing you again. Take care. Pop by again next time. Okie dokie. Phonics. I like it. Okay, suspend. We are trying to... Suspend takes arguments. Our definition of suspend. Right, it takes a few arguments here. Looks like a continuation. An IREP and a couple of a try and a couple of continuations. So that is definitely not enough arguments in that area. I feel like this is part way where the paper kind of is just flying through definitions and not really filling things out. But let's try and see if we can get it to go. So it wants this to be a list of eval tree, but we got eval tree refs in ST because that's what we changed eval tree to contain. Right. I leave that branch undefined for the moment. Is that because we need to update our definition of lazy? Or try? Oh, no. The parameter here, eval tree. We probably want this to be a ref. Okay, and subterms now as well. Okay, let's check the paper here and their implementation of things. Okay, so they use or IOREF. And what's the susptio definition? Grab my pen here. The data structure is already evaluated. We either succeed or fail. The data structure is not yet evaluated. We add a suspended computation with the corresponding IOREF within the eval tree. The action is to be performed when the constructor is evaluated to head normal form is the same, matching again p nil of rx. In the definition of susptio, the action within the IOREF is extended accordingly. Okay, so I think they just create this new definition, replacing suspend. This one here. And we should implement that. So use it here in p nil as well. And I gotta get my mouse back. There we go. There we go. Okay, yeah, and then new type try A and our continuations. Okay. Let's go over there. Just quick review here. So we implemented the new type try here with the success continuation, the fail continuation IO. We got the functor, the applicative instance, and the monad all lined up. This from try function. This new version of fail, which just runs the failure continuation. And okay. And then nil. Okay, we haven't gotten to updating nil yet. So try, fail. You know, it's implemented in terms of suspend TIO, so we need to implement that. That takes the IOREF, try A, the success continuation, fail continuation, and IO. So we got the AREF, the try, Success, fail. We get our IO ref. We write to it. Write to the A ref. By running the IO action, taking the new try, or taking this try that we're passed in, which matches what they're trying to do here. Yeah, and then we pass the success and failure continuations through. So essentially we do nothing. We suspend. Okay, so then p nil, or nil in our case. Let's go there. Lazy A to try. This try is no longer try unit. Now it's going to be a try of lazy A and a lazy list of A. Okay. The base case here is going to be failed. This one, eval, where we have an EX and an EY, or an eval X and EY. Some computations and return pure, and this EY of Y. Then on the uneval case, we have the aref V. We try to suspend the aref. And the pecans. Oh, sorry, this is pecans. I'm supposed to look at the wrong one. That should be pure unit. I was looking at the wrong one. Okay, so they want this to be like this. I guess we already had that, didn't we? Okay, try suspend aref nil rx. Okay. Eval should have 2. What's the problem? Our eval tree is still one argument, yeah. Okay. Theirs is still one argument as well. And then we do that. Obtain changing try, or trigger monad, instance for it. And fail. Nil. Yeah, I don't know why their code has 2 parameters for eval. And their updated version of nil. Should be only one. Should be unit. Okay, that compiles at least. I think this also has, that's p-nil. Now we're on pcons. Okay, now we're on the cons. Okay, I called them subterm x and subterm y. I remember that. X, x, y. Okay, so in that case, we're supposed to return a lazy, what's this one? IOF eval tree with eval tree. X. And we have a lazy list of A here. And I didn't see any changes they wanted us to make to the IO, to the lazy type. It's the observation type class. Observe. You know, sometimes they say you really just got to go through a paper and like implement it yourself. Because maybe if you just take it for what it is and you don't try it out, maybe you find some things that were overlooked. Yeah, I don't see any changes they want us to do to lazy. Except that they define lazy A as an eval tree of A. Maybe ours is the same, except as a new type instead. So the eval tree there should be right filled with eval tree refs and non-eval tree refs. Okay. Okay, so we couldn't match IO ref eval tree with just eval tree when we pull out the subterms of eval, because eval type, yeah, those are going to be eval tree refs. And going into this, the A here, well, we don't really say, we just say that they have to be the same type. Which means they need to be eval trees. So I think if we just stick the eval constructor, or we have to pull these out. Okay. Try lazy A and lazy list of A. If this doesn't work, because these need to be we need to return a tuple of lazy A and lazy list of A. And it kind of would work in the paper because in the paper, lazy is defined as a type alias for these tuples. Why does the subterm here not match up with this type? Okay, yes. Okay, so it's an eval tree ref. You want it, you determine, the inference determined that it's got to be an eval tree. Because this tuple here if I make this an eval tree ref, the lazy computations are then going to hold an IO eval, an IO ref eval tree. That's essentially what this is here. Right. Just replace it, eval tree. Forget the type alias. We need the type alias because when we construct one, we got to initialize that IO ref, and it's kind of like a tree of these evaluations in these IO refs. Okay, so I think the definition of lazy, that means lazy should probably be an eval tree ref. Okay. That makes that impossible. That and that. And all of these, because we can no longer match on the constructors. So I don't think that's probably not the right idea. I think what we need to do is unfortunately do some unsafe IO in order to unwrap, in order to evaluate these subterms to get the eval trees within. And then we can construct the new lazy A's from those. Unless, well, try is our monad now. Which is an IO. It has this function, this coroutine inside that is IO under the hood. The success continuation, the fail continuation. Oh, did I? Oh, sorry. No, not exactly what I was thinking. Okay. I got it. This isn't the right code yet. Right, because this is just an IO action. So we got to get the IO ref out. The value out of the IO ref, so read IO ref. Subterm Y like that? No? So we're trying not in IO. Okay, so try isn't technically a monad in the sense of like a transformer where it's built on top of IO. It's just got this function inside that has IO at the bottom. So that's not the right approach. Mm-hmm. Yeah, that's not what I was expecting here. So let's turn that into a hole. Turn that into a hole. And see what we can do here. So we want an eval tree here. We have an IO ref with an eval tree in it. We're not in IO technically. Don't think it would be a good idea to read IO ref unsafely in cons. What else do we have? Can we do with them? Now, that was interesting. This next definition down here is doing an IO actions inside of try here. So it's creating a new IO ref and is doing this or IO ref, which takes our continuations and does an IO action as well, an IO unit there. So that one would be fine. Their interesting implementation of the immonad instance here. Okay, so if there exists an alternative for a failed assertion, for example, by non-deterministic branching in our parallel OR, then the success continuation can discard the current fail continuation. Now we're ready to define the monad instance for the new type try. Okay. Let's go back to that. Because I'm used to using transformers, which I guess this kind of predates maybe. This is an interesting pattern I haven't seen before. Try as IO. So that'll be this function as IO. We'll have this type. Bound to some function f. So if we try to construct such a try, we take the success condition and those as parameters, yeah. And we call as IO, remember this function up here, with our new success continuation. From try f of x, sc, sf, and a new fail continuation. So I guess that's what they mean by sfc. The successes fail continuation. There. Breno Shack, you are banned. I do not appreciate follower spam and stuff. Okay, out you go. Only homegrown here. You know? Friends and followers. Only. True followers. Alright. Where were we? So then, fail continuation. And the pure instance for this. Or, no, that's in the applicative. The pure applicative in this pure of x, we got try sc fc sc fc x. And then the applicative apply. And we derive the functor instance for it. So that should be our complete monad there. And then interesting that they use from try here. Okay. So like suspend can go and do IO stuff because it's in IO. But cons is in try. So I'm wondering how this paper, is it a mistake that they think they can run? Well, they don't think they can run IO refs in here, but it looks like they think they can. That's our definition of assert. And that should be the complete part of the assertion stuff. And this other stuff is like bonus. things. Yeah. No, I don't think you can define the pattern combinator in this way. The types are not lining up. Right. If we can discharge that IO ref, we can read the value out of it, this eval tree. We would have something of type eval tree to stick in that hole. But we don't. We don't have an IO action here, so we can't read it without doing something unsafe. So what did you mean? Well, gotta be a missing definition of lazy A. Or, no, I'm just taking shots at the dark here. But, what if... it couldn't be that the new type construction that we use has anything to do with it. Insert checked, no that. That's the only definition of lazy that we have. But once we introduce the eval tree and then the eval tree ref, type in the later section, that breaks lazy here. And if we put lazy tree refs inside lazy A, that breaks a whole bunch of stuff. But maybe it's stuff that we don't care about. Well, it also made it also made the pattern matchers here that we're trying to come up with impure. Which is what we're dealing with right now. Because the eval constructor here has IO refs of tree, element tree. Oh, okay. Actually, yeah, maybe maybe it's a skill issue here. So they call it eval R here, the constructor. And that contains the eval tree refs. Okay. So an eval tree ref is the IO ref of the eval tree, but the eval tree is still... Oh, but the eval tree still has the refs inside of it, so it doesn't matter that the constructor is named differently. On eval R. Because now nil still can... They're still destructuring on eval, not eval R. Yeah, we implemented all of those. Okay. Okay, so generating eval trees. To generate evaluation information for data structures, use the idea of observations. All values for which an assertion is specified are observed. An observation constructs a corresponding eval tree, representing how far the data structure has been evaluated. The key idea is the context of a computation demands head normal form. Whenever such a head normal form is computed, we extend its eval tree by means of a side effect. This means an uneval leaf is replaced by eval with a list of uneval, where the number of unevals within the list is equal to the arity of the constructor of the head normal form. Because we construct and use eval trees in program parts that are not linked by data flow and for efficiency reasons, we use mutable references in our new eval tree representation. With this representation, it is not necessary to descend into the whole data structure when extending it in a leaf position. Instead, we can directly update the leaf. Observable data types are represented by the following class. And we demonstrate how an instance of this class can be defined by means of its list data type. Okay, like so. So whenever the context demands the evaluation of an observed value, the corresponding node in the eval tree is extended by means of the function make eval tree constructor, or muck eval tree cons. Programmer short speak, you know? Furthermore, observers are added to the not yet evaluated arguments of the resulting constructor. These observers extend on demand the IO refs returned by make eval tree, aref, and bref, which are also added to the new eval r node within the eval tree. The initial observer can be added with the function observe. Takes an observe A, takes an A and an IO action, which returns the tuple of an eval tree ref and A. This function is called whenever an assertion is added to a data structure, as discussed in the next section. On top of these functions, it is possible to define a late in contrast to prompt implementation, blah, 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 blah. Okay. So is this like in addition to... And we still need to have like the pure versions of these. And somehow we're gonna connect these things up in some way through observations. So I called it make observe so that my type class can just call it observe. Okay, makes sense. All right. Promptness. So far, our assertions meet two major goals. They respect the laziness of the program, they provide non-determinism. However, we still want our assertions to be prompt for the following reasons, which we all know and love. So, the implementation shall suspend checks on unevaluated parts of data structures and directly awake them when those parts are evaluated to head normal form. So preparing the eval trees. We're checking an assertion. Many checks have to be executed concurrently on different parts of the tested data structure. Many of these checks will have to suspend because specific parts of the data structure are not yet evaluated. Makes total sense. We store each suspended check in the uneval leaf associated with the part of the data structure that it is suspended on, so that the checks can be executed when the data is demanded. Several checks may be associated with the same part. Hence, many suspended checks may have to be stored in one uneval leaf. A check does not return any value. It may just raise an exception. But it reads IO refs to read the growing eval tree, and hence it is of type IO. Checks may be added to an uneval leaf at different times. We simply compose all checks for one eval leaf sequentially as an IO action stored within an IO ref. Okay, arbitrary sequential composition works because we assume that all checks terminate. We redefine eval tree with a reference containing an IO action. Okay, so they don't want like two different... What I was thinking is that maybe this paper wants us to implement an eval tree and like an IO ref eval tree. But it says they redefine the eval tree with a reference containing an IO action. So how then do we do those... the implementation of the view pattern matching things... Pattern matching combinator things don't really work. Like, that makes sense. And then for the construction of the new eval tree, we just have a constructor here. Sets everything up. That's all fine. We implemented tries a list of maybe values or computation values. However, for implementing promptness, we have to compute the assertion check step by step whenever eval tree is extended. Hence, non-determinism or coroutines through continuation passing style is a more appropriate means of implementation. We have a success continuation and a fail continuation, just like continuation-based parser combinators. The success continuation must take a fail continuation as argument to support non-determinism. So like, all right. We already established that checks are of type IO. They have to be an IO. Okay. So that's what our fail continuation and success continuation looks like, and we have new type try. We have all of that. We implemented all of that. So I think these definitions in the paper here for p-nil is just not right. It's wrong. Or somehow it works for p-nil's case. Because we don't, in p-nil's case, we don't actually look at any of the arguments. I don't know why it's 2. The type, even in the redefinition, is only 1 argument. For some reason, they list 2 here. But we don't look at them, so we never evaluate them. So if they're IO refs, it doesn't matter to p-nil here. So similar to constructing success continuations by means of return, it is handy to have a function fail t for constructing fail continuations. We have that as well as fail. We have one ref here that we pull out, ref, and we construct a try with suspend, which is fine here because ref is an argument to suspend. And so we don't actually try to run that action in an IO context. We pass it forward pretty much untouched here. That makes sense. Now, if the data structure is already evaluated, or at least, I don't know if this nil thing, well, it makes sense in a way. It's cons that's bothering me. So if the data structure is already evaluated, then we either succeed or fail, yes. So if the data structure is not yet evaluated, we add a suspended computation to the corresponding IO ref within the eval tree. The action to be performed when the constructor is evaluated at normal form is the same matching again. P-nil Rx. In the definition of susp TIO, the action within the IO ref is extended. Okay, so in this definition, they do this thing called extending. We're supposed to extend the IO ref. Right, so we read out that IO ref. We're in an IO context, so we can do that. And then we write IO ref by evaluating that action, pretty much ignoring its result, just continuing on the next thing. Construct a new try. And, or no, from the try, we get its action, the success continuation, the fail continuation. Similarly, we can define the pattern combinator of pcons. Can we, though? Maybe what the dual arguments are supposed to be. Maybe the definition is supposed to keep both the IO refs and the computations. I wonder if that's the case, because that would work. This branch would work. Maybe fail would work. This one can't. So I wonder if eval tree should have a second argument. That isn't the IO list of IO refs of eval tree, but it's just the list of the computations. But we need to input A there. Does that make sense? Or no, sure. If it's in, should be the different order, but I wonder if that's what the intent is here. What does this mean now? Well, unfortunately, it kind of means that like these two lists don't really have any relation to each other. This is a list of IO refs of eval trees. All right, this sort of idea of suspended computations that we can evaluate on demand as we need them. And this is a list of computations, and so we could construct easily an eval here from the eval constructor with like two lists, one list with a list of computations here and like one that is like empty, the empty list. Right? This would be a perfectly valid construction of eval tree. With computation result A, whatever. So like result 1, result 2. Right? So it's a bit odd, but if we don't let the user necessarily construct the eval tree directly, we provide smart constructors and we provide a proper algebra for working with these things, then presumably what they might have meant is that when we evaluate some action in here that returns a result of some like int, right, that we appended to this section here the results of those computations. You know what I mean? Like, does that... Maybe that's what they intended? They're trying to tell us here? This or-IORef function. This or-IORef function. I'm going to look for some more clues here. That this might have been the intent. So or-IORef takes an IORef of bool, a fail continuation in IO. So when constructing a try here, we're giving this continuation. And while we're in an IO context, so we can read the ref. Where's this from? That's just true. And then we try of X with the success continuation and or IORef with this true thing and the failed continuation. And then Y, see, with the same thing. So we evaluate both branches, basically. All right, we evaluate this, the continuation in here and the continuation in here. I'm not sure why we need to pass this IORef bool here. Because in this body here, we read the IORef here, and if B, which is going to be always true, then we write the IORef ref false. Oh, okay, I think I understand now. Because it's an IORef, it can be mutated, right? So what this is doing when we do IORef in this part, right, is if we read the IORef here, and if it's true, so maybe on the first evaluation it is, then we write to it the value false, else we call the fail continuation. The fail continuation passed in here. So I think what this is doing then is we're going to try this branch. Right, and if this branch evaluates first, we write to the IORef false, and then this one tries to evaluate the same thing, but v is going to be false, so it's just going to go to the failure continuation on this side. Either or. And so they can be done in parallel. The sequence doesn't matter. They can both be done at the same time. Just one of these is going to do their continuation, the other one's not. Okay. That's fine. So what am I looking for here is something that shows that we're collecting together somehow the computation values inside the eval tree and not inside these IO refs. Something that uses that argument that so far has been ignored in those combinators. So in this case, we have two tries, so two continuations, f and x, with their own success and failures. I'm constructing a new one. So the fref, that's the left side here, I guess, colloquially, will be a new IROF with list, and same with x. And then ref. I guess we're using this trick again. So to get to true initially. Okay, so now we call at the f continuation that we get from the first try, and we update the IO ref by appending a cons. Interesting. That might be it. So we update the IO ref. Which one? fref. And we're going to pass in this constructed list of tuples. ffc and f prime. So the success continuation of this branch, whatever that value is, and f prime, the failure continuation for that branch. Then we read x's from xref. And we do this monadic map. Function over x's. So we map over x's. We're taking the x continuation x, the success continuation sc. It's coming all the way from up here. We're getting the value of ffc and xfc, passing in the failure con on x. And then we're doing the and ref fc. So I think what this is doing here is it's evaluating both sides and ensuring we get both results. Like neither one hits a failure continuation. I'll give my markings here to do. Right, and we do it by this and IO ref bit here, which takes the value, and if v, then we write IOF false, and then we call fc the failure continuation. Otherwise, we return unit. So what fref and xref are consing together lists. Okay, and one of these It, this one's kind of dense. So the try A and try B part. Okay, so we're going to evaluate the try A. We're going to get that value, and we're going to pass it into this first one here to get a B, and then we'll return a try B. That lets us implement this AND assertion here. A very tricky way. So that if we get x1 and x2, we return unit, we're good. With t1 and t2. So the explanation for this is the computation of both arguments of this may introduce non-determinism, that is multiple values. So that's why we would use a list. The arguments, okay, the tries. Whenever a new value is produced within the success continuation, right, they may... So the try might be working on a data structure that a part of a data structure that produces more than one value. Okay, so that's why we need the list. And we, besides the different, we extend the corresponding list in that branch, fraf or xraf. And then besides the different values, this list also contains the corresponding fail continuations within a pair. Furthermore, we directly apply a new function to every already computed argument in the success continuation of f, as well as every stored function to a new argument in the success continuation of x. Thus, every function is applied to every argument exactly once. I think that means this term here, this expression here, down below, x, f's, and the fail continuation. Okay, so and if any computation fails, we update the Boolean value in ref to false and directly continue with the fail continuation. Then if the other coroutine fails as well, the IOREF already contains false and it stops immediately. Like for the disjunction operator, the fail continuation is executed at most by one coroutine. Finally, we need the definition of assert. Okay, so this is where we evaluate observe of our x. So the arguments to observe will be a string. I'm guessing that's going to be the label, yeah. Our predicate. So this is what the user is going to input, is going to write. Instead of like just an expression that evaluates to Boolean, you're going to give us a function. We got a lazy A to assert. The A, the value of the expression you're wrapping in this assert, which returns in the case where this is true. So we do some unsafe perform IO. We observe. Let try of check equal p et of x from the observation on x. And we check. And then we have const. It looks like two expressions here. Const assertion succeeded or fail assertion failed. Return x. So after installing an observer for x, we directly start the coroutine check for the asserted property p. Usually this coroutine directly suspends itself. Its success continuation ignores its fail continuation and simply prints the asserted succeeded. The fail continuation aborts the whole computation, reporting the failed assertion. We have to pass x, not the observer wrapped variant x prime, to the property p, because partial value of x prime is only available after all the necessary assertion checks have been performed on it, as shown in section 2. The real implementation reports a failure with a highlighted presentation of the wrong value, which we discuss in the next section. Furthermore, success messages are written to a file to avoid conflicts with the program output. To provide a comfortable library, we provide some further functions on assertions like negation, implication, and assertion variants of standard functions such as elem and any. Interesting. So here we actually have an eval now with 3 arguments. But it's still, they're not interesting, unfortunately. They're not what I hoped they would be. Looks like it's eval position string. This is for the air pretty printing stuff, so it's carrying state here. Extending it for functions. Okay. Yeah, I think we're out of luck on this one. Paper isn't going to help us. So I didn't see... I saw where it was like evaluating and consing together the evaluations, but not the resulting computations. So I don't know how we can implement this. It's just not possible. Only sneaky bad stuff can do it. Or maybe we can do it with this. What we call it, XE. Call those refs. That's what they are. Do. Oh, we need to undo that. Do. That's fine. Get rid of this. And the type parameter. And maybe the parentheses. Yeah, let's go past those for now. Okay, we're in IO right now. So now we do have subterm X and subterm Y. Maybe this is the way it's supposed to be written. So then we need the pure lazy subterm X and X with a lazy Sorry, that was very confusing for me. Subterm y. X's. And the problem with this, we expected to type unit, giving it, returning that. No, we're expecting a type of this. Oh, yeah, sorry. Interesting, okay. That's an IO unit because the continuation in try returns an IO unit. And for some reason, in this silly thing, it wants... The silly combinator wants it to be this tuple with lazy A and lazy list of A. I don't know if we even use pecons again. Maybe this is not super necessary. Yeah, it's not in the continuation. Like, if we couldn't if we wanted to. Right? What could we even put there? Has to be a lazy list of A and lazy list of A, but we can't get those without doing some IO here to read those refs. So I'm gonna call bankruptcy on this one. Possibly this one. I think that maybe these combinators they need to be rethought out. Because that just doesn't make any sense. Well, the only way that could make sense is if the definition of pry is polymorphic. In its continuation. Which they specifically write here that it isn't, right? It's like hard-coded into from try, which is hard-coded into its monad instance. Yeah, so I don't know if we can, those pattern combinator thingies can even be used, can even be written. Doesn't look like it. Okay, so let's try the rest of that stuff then, because we're getting pretty close to a point where we could maybe try using a bit of this library. Almost at writing assert. Okay, so ignoring pecans. We're trying to implement power disjunction. This is going to be different now. We'll have a try of X. Do the power disjunction and a try of Y. And here we do our continuation. Reading the IO ref, or creating a new IO ref of true. And then Y, or IO ref of FC. We haven't defined or IO ref, so we'll just take that there. Fail cont, IO unit. So we read the ref. And then if we have V, then we write IO ref. False, else, FC. Okay, that looks okay. And then we do this sort of parallel apply. Which we have to redefine. Take the success continuation, the fail continuation, and we go into it again. And then the two branches, F. Cons. On FREF. X's, we read the IO ref. And then it map M's over. Taking the C side of things. Yeah, SC. FFC, then XFC. Passing through F prime X. And X's. Then we do X. It's almost the same looking on both sides. Balancing issue here. Yeah, so hang on. We got the balancing issue with some parentheses. That balances there. There. We got open. So it's 1, 2, 3, 2, 1. Okay, that's probably the balancing one there then. Yeah, I was wondering there. I'm like, wait a second, I think I dropped something here. XFC. Taking the success, FFC, then XFC, and then F prime X. X's. Yeah. Not in scope update IORef. Okay, we'll have to fix that. And we haven't blended and IORef yet. Sorry. F. There's probably some name shadowing possibly going on in here. Something like that. Update IORef. I'm curious. Google. No, it isn't a function. Maybe modify IORef. Maybe that's what they meant. Yeah, that's a good point. So the documentation for IORefs, we have atomic IORefs now to do atomic updates. Maybe this paper was written that preceded it, or it's just not heavily tested for that sort of environment. They're just kind of explaining the concept here. So we're probably going to need atomic or modify IORef and really think about how this code is being used here. But you take the IORef first and then the function. Not FF, it's FFC, not FFX. Okay, that works. And for the X side, FC there. And change these to XFC. And then we'll do, does it matter? FFC to XFC. X up there. Okay. There should be X there. There we go. Now we just need to implement and IO ref. Whew. So we take the read the IORF value. And then if that value is true, write IORef ref false and call the failure continuation, else just return. Okay. Finally we can implement assert. All right, let's try it. Observe a string, a lazy A to assert, an A and an A. That's going to be our label, our predicate P, and our expression X. And we're going to unsafe perform some IO for you. You're welcome. Then we get the expression turn X prime here from observing X. Try and check P, ET, and X. No, X. Oh, okay. Check. I don't know if we've implemented that yet, but hopefully we have. Cluster len. Assertion succeeded. A lot of parentheses in this code. Check open, const, open, put len, open. Assertion succeeded. Label. Fail. Assertion failed. Label. Okay, for some reason those not looking good so far, but hopefully we can fix it. And then your X. Probably fail continuation. They probably meant like the prelude fail or control.monad. Let's just change that to error. Interesting. Okay, that's where check comes from. It's from there. Success continuation unit, right. Where did we define those? Success cont A. Failed continuation sum A and then IO unit. Okay. So it wants something of that shape for this hole. I guess that's what const was in order to ignore the failed continuation. Then we get sum A. Doesn't matter what we want. Let's just put strlen assertion past label. No, this is not observe, it's make observation. Maybe make observe. What did I call it? There we go. Gotta wrap it in lazy. Yeah. It looks like they rushed kind of the end of this paper. So they want an eval tree ref. Eval tree. We know how to. We have a constructor for all that, right? At least we have that. Make eval tree. Or an empty uneval ref. Maybe one of those. No. We get it from make observation. Make observe. Yeah. So that should be an IO ref. Oh, right, we're back into the whole lazy is expecting an eval tree, and we have an eval tree ref. So that's probably got to be what's missing there. I'm going to type lazy. Like, now that's fine. This. Now that's fine. Okay. Yeah, that borks all of this. Because this X here is supposed to be continuation for try here. And we want a function from A to B. But x prime is an A. F prime probably has the same issue. Yes, F is such an A to B. X is trie of A. So this really should be F. No. Yeah. Let me comment this one out. This one is fine. Yeah, you were busted a while ago. Don't think we need you. Your demonstration code. Some good warnings, thank you. Replicate M instead of sequence. Yeah, I agree with that. Let's do that. And B, right IO ref false, FC. And then nothing else, no errors. We're all good. Ah, okay. Let's get rid of the commented out stuff. No, see? No. Haskell's going a little... This is... from try. Let's try taking that type. Thanks, GHC. Pop that in there. Clean that up, should be A. Not used. Not used. Okay, that could be... Right, okay. Yeah, because we haven't done that. this. Where was that? F's. And map them. Name shadowing here. Okay, does that work now? That works now. Okay, get rid of that. Okay, discarded a result. We meant to do it intentionally, we can do it like that. Probably meant that. Okay, cool. All right, now how do we use this thing? Let's load it up into our REPL. Yeah, I don't care about those warnings. Okie dokie. Let's do something simple first. So we have to give it a function lazy a to assert. Oh, I see. It's our structure. Okay. Let's just ignore it and... Or what can we do with L? Something with L. That's our A, our expression A. Interesting. I don't know what we can put in there exactly. Something of assert. Or try. Success continuation A. Or do we have to write our, maybe we have to write our own combinators for everything in here. Oh, okay, we're getting ambiguous type error from GHC at the moment. We're running low on time. What's... oh, this is ambiguous. Okay, now we need an instance of observe int in order to use it with assert. I think that means we're gonna have to like implement a bunch of assert instances for constant common types. Interesting. Okay, well, we'll have to look into that. I'm gonna push up the changes. We're staged. Let's commit to committee commit. Right. Hang on a second. Da-da. Right, so I'll create a commit, we'll push this up, and I'll play around with it. I don't know what we'll do next week. As I play around with this, I'm going to like try and figure it out, and maybe I'll make it into a library, but I'll probably just do that at some point. We'll do something else next week, depending on how much I can get to. But thanks for joining me tonight and hanging out. All the code for this is going up on GitHub. If I can get the commit made. Okay, and this is Disco. And this is my little repository for this code that you've seen tonight. I'm trying to implement the code in this paper. I'm trying to understand how to do lazy evaluation and lazy assertions in Haskell. So pretty neat so far. Hopefully it'll be practical, but definitely learning stuff. And yeah, so I'm Agent Ultra. I'm Agent Ultra on GitHub. I'm also on the Fediverse, on the Mastodon server at types.pl. Agent Ultra. I'm also agentultra.com. You can check out my site, get all my links to there, including my YouTube channel where I back up the VODs for this stream. And if you want to go back and follow old ones there, you can go there and check that out as well. Give us a like and a subscribe, leave a comment, or follow us here as well. You can follow me here and set up your notifications. You get notified when I go online and do a stream. Normally I do these on Wednesday evenings at about 10 after 8 in the Eastern time zone. So if you just want to write it down and follow it because you don't like notifications or whatever, I don't judge, but you can put that in your schedule there. I will see you next week. It's been a pleasure. So yeah. Also, check out the links above my head. It goes to declarative.tv, where there are a lot of other cool streamers who are doing things in languages like Erlang and Haskell as well. And they're doing streams there as well. And there's a link to a Discord server that you can go to. And there's a channel on that server for this stream, so we can chat about your projects. What are you up to? What sort of Haskell do you write? Are you interested in Haskell and maybe haven't started yet? Or just ask questions about the streams that you didn't get a chance to because maybe you're watching in a different time zone. Anyways, it's been a pleasure. Thanks again for watching and following along and hanging out with me. May all your monads be free and your types always check. And we will see you next week, hopefully. Take care and happy hacking.